Hello everyone, welcome to my class. In my previous video, we discussed quantum mechanical model of an atom and before that Schrödinger wave equation. Now today we will talk about quantum numbers. So the solution of the Schrödinger wave equation gives us three constants and these three constants are called quantum numbers. So quantum numbers, if we have to explain, we can simply say it is the address of the electron. Like all of us have got some address. Same way, if we want to locate the electron in an atom, we need certain numbers and those numbers are called quantum numbers. So what are quantum numbers? Simply the set of four numbers which gives us a complete information about the electron in an atom. That is, it tells us about the energy, the shape, orientation and about its spin also. Now quantum numbers are actually four in number. There are four sets of numbers. But the fourth number is not given by the solution of Schrödinger wave equation and it was independently given by Uhlenbeck and Gauss-Schmidt. So they gave the fourth quantum number called spin quantum number. So there are total four quantum numbers. Number 1 is the principal quantum number denoted by n. Number 2 is the orbital angular momentum quantum number, also called azimuthal quantum number, and it is denoted by L. Number 3, magnetic quantum number and is denoted by Ml. And number 4 is spin quantum number and is denoted by Ms. Let us talk about the first quantum number, that is principal quantum number. As I told, it is denoted by the letter N and it was given by Bohr. Bohr gave principal quantum number. It determines the mean energy level in which the electron revolves or is revolving. And if we know the value of the energy shell, then definitely we can determine the energy of the electron in that particular shell. Remember, larger the value of this quantum number means the electron will be quite far away from the nucleus. Hence, the size of the atom will be bigger. When n equals to 1, we call it as first shell called K shell. When n is equal to 2, we call it as the second shell called L shell. When n equals to 3, n equals to 4, M, n equals to 5, O, P and so on. That means n can have any value ranging from 1, 2, 3 and so on, but it cannot have value less than 1. Means n equals to 0 and n equals to minus values, negative values, they are not permissible. And as the value of n increases, then definitely the energy of the electron in that particular shell increases. That means the energies of the various shells follow the sequence. K will be having minimum energy and then comes L. L will have higher, M will have higher than L and N will have higher than M and so on. So what is the information conveyed by principal quantum number? Number 1. It gives us the number of electrons in that particular orbit or shell according to the formula 2n square. But remember, no energy shell in atoms of known elements possess more than 32 electrons. Put n equals to 1, that means 2 electrons are possible in first shell. Put n equals to 2, that means 8 electrons are possible in the second shell. Put n equals to 3, that means 18 electrons are possible in the third shell and so on. Number 2, it gives us angular momentum of electron, means it helps in the calculation of angular momentum of electron. Number 3, it gives energy of electron. According to the formula, En is equal to minus 2 pi square me4 z square upon n square h square. So according to this formula, we can find out the energy. And if we can find the energy, that means we can also find the radius of that orbit. How? Using the formula Rn is equal to R0 into n square upon z. So that's how distance or the radius can also be calculated. Coming to the second quantum number called azimuthal or subsidiary or angular quantum number. This angular quantum number was given by Sommerfeld. Now, within the same principal shell, there are number of subshells or sublevels of energy. As a result, the number of electronic jumps increases and so is the number of lines. That means this azimuthal quantum number helps to explain the splitting of the main line in the spectrum. Azimuthal quantum number, it gives us the information about the subshell of an atom. It is represented by the letter L, and it can have values ranging from 0 to n minus 1, and for any value of n, L can have total values n, and the highest value will be n minus 1. For example, if we put n equals to 1, for n equals to 1, L can have only one value, that is 0. Put n equals to 2, we can determine the value of L. When n equals to 2, the values will be starting from 0 up to n minus 1. So that means only two values are possible, 0 and 1. Put n equals to 3, means for the third shell. Put n equals to 3, so values will be ranging from 0 to n minus 1. That is from 0, 1, 2, but 3 is not possible because maximum and the highest value is n minus 1. 3 minus 1, that is 2. So 3 values are possible, 0, 1, 2. Similarly, for the fourth shell, put n equals to 4. L can have values 0, 1, 2, 3, but not 4. Why? Because maximum value can be 4 minus 1, that is 3. So depending upon the values of L, that is L equals to 0, 1, 2 or 3, different subshells are designated. When L equals to 0, it refers to S subshell. L equals to 1, P subshell. 2, D subshell. 3, F subshell. So these notations are actually the initial letters of the words sharp, P principal, D diffused, F fundamental. These words were actually used to describe different spectral lines. Put L equals to 4. This is called G subshell. If we put L equals to 5, then it will be called H subshell. So first principal shell can have only one subshell. Second principal shell can have two subshells, 0 and 1, S and P. Third principal shell can have three subshells, S, P, D. Similarly, fourth shell will have four subshells, 1, 2, 3 and 0. 0 means S, 1 means P, 2 means D, 3 means F. So there are four subshells possible for the fourth shell. So remember, the energies of different subshells are in the order S will have minimum energy since it lies closest to the nucleus. Then comes P, D and F. Now, the S subshell can accommodate at the most 2 electrons. P can accommodate 6, D can accommodate 10 and F can accommodate 14. We will calculate these number of electrons but after certain time. Angular quantum number helps in the calculation of orbital angular momentum, that is capital L, orbital angular momentum, and it can be calculated using the formula h upon 2 pi root L, L plus 1. So h is Planck's constant. Put L equals to 0 in this equation. So if L equals to 0, that means the capital L will come out to be 0. Put L equals to 1. That is h upon 2 pi root of 1 plus 1. That is root of 2h upon 2 pi. Put L equals to 2 in the equation. You will get the value of L is equal to root 6h upon 2 pi. So maximum number of electrons in a subshell are always equal to 2L plus 1. 2L plus 1. Let us now talk about third quantum number called magnetic quantum number. This quantum number is required to explain the fact that when the source producing the line spectrum is placed in a magnetic field, each spectral line splits up into number of fine lines, and this is called Zeeman effect. Zeeman effect. In order to explain Zeeman effect, Linde proposed that an electron, because of its angular motion around the nucleus, produces an electric field, which in turn leads to magnetic field. And the magnetic field of electron will be attracting, or it will be behaving like a tiny magnet. As a result, electrons present in a particular subshell acquire certain specific orientations in space, and these are called orbitals. These specific orientations in space are called orbitals. That means magnetic quantum numbers tells us about the orientations. About the specific orientations means it tells us about orbitals. So value of m tells us about the orbitals. Magnetic quantum number is denoted by the letter m, and therefore for a given value of L, it can have values ranging from minus L to 0 to plus L. For a given value of m can have values ranging from minus L to 0 to plus L. For every value of L, m has 2L plus 1 value. For example, for L equals to 0, m can have only one value, that is 0. That means S subshell has got only one orientation. So only one orbital for S is possible. Put L equals to 1. L equals to 1 means we are talking about P subshell. Well, L equals to 1, m can have three values. How? Ranging from minus L, that is minus 1, to 0, that is 0, up to plus L, that is plus 1. So for L equals to 1, m can have three values starting from minus L to 0 to plus L, that is minus 1, 0, plus 1. So that means P subshell can have three orbitals along x-axis, along y-axis, and along z-axis. For P, Z means when the P orbital is along z-axis, P, Z, value of m is fixed. That is, m will be 0 for Pz. M equals to 0 for Pz. And when m equals to minus 1, we can refer it as Px or Py. Similarly, when m equals to plus 1, we can refer it as Px or Py. Means we can interchange these values, but for m equals to 0, we refer it as Pz orbital. So these are the three orbitals of P subshell. Similarly, put L equals to 2. When L equals to 2, we can have total 5 values. According to formula 2L plus 1, we can have total 5 values starting from minus L to 0 up to plus L. That means we have to start from minus 2, minus 1, 0, plus 1, plus 2. So means D subshell can have 5 orbitals. Similarly, L subshell will have 7 orbitals or 7 different orientations starting from minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Now again, for L equals to 2 means for d subshell there are 5 d orbitals: dxy, dyz, dzx, dx square minus y square, dz square. These are 5 d orbitals: dx, y, dy, z, dzx, dx square minus y square, and dz square. So these are the 5 d orbitals possible. Again, when L equals to 2, m equals to 0, it refers to dz square orbital. dz square means when m equals to 0 for L equals to 2. It's a fixed value. Fixed value. So after this, remember one thing. These orbitals of the same subshell have equal energy. And these equal energy orbitals are called degenerate orbitals. But in the presence of external field, this degeneracy is broken. Means all the orbitals of the same subshell will acquire different energy. This causes the splitting of the main line into the fine lines. Coming to the last is spin quantum number. Spin quantum number. Spin quantum number represents the spin of the orbital. The electron in an atom not only moves around the nucleus but also spin about its own axis. So this number gives the information about the direction of spinning of the electron present in any orbital. This spin quantum number cannot be obtained from the solution of Schrödinger wave equation but was given by Goldschmidt and Uhlenbeck, and it is denoted by the symbol S or ms. Since an electron can either spin clockwise or anti-clockwise, so that means for a given value of m, S can have only two values, either plus half or minus half. Can also be represented in the form of arrows, either arrow in the upward direction or in the downward direction. So the value of S can be used to find out the spin angular momentum. Spin angular momentum. How? Using the formula h upon 2 pi root ss plus 1. H upon 2 pi root ss plus 1. This is how we can calculate spin angular momentum. And the maximum spin of an atom can be simply calculated using the formula half into number of unpaired electrons. Mind it, unpaired electrons. So this quantum number is not the result of Schrödinger wave equation. Next is, this quantum number helps to explain the magnetic properties of the substance. Because a spinning electron always behaves like a magnet, a micromagnet, having some magnetic moment. So if an orbital contains two electrons, the two magnetic moment opposes and cancel out each other. So in an atom, if the orbitals are fully filled, then net magnetic moment is 0 and the substance is diamagnetic. But if some half-filled orbitals are present, then the substance will have net magnetic moment and is paramagnetic. So here is the complete representation of the electronic distribution in first 4 shells. And here I have represented in the form of N means shell, L subshell, then how to denote that particular subshell, then the orientations and the number of orbitals possible. Let us sum up with some data. That is, maximum number of orbitals in a subshell are always 2l plus 1, maximum number of orbitals. Maximum number of electrons in a subshell 4l plus 2 means double the number of subshells. 4l plus 2. M can have total values 2l plus 1. 2l plus 1. The spin angular momentum can be calculated using the formula h upon 2 pi root ss plus 1. Angular momentum can be calculated using the formula h upon 2 pi root ll plus 1. Spin quantum number can have only two values, plus half and minus half, because electron can only spin either clockwise or anti-clockwise.